Hi, I'm Julie, and I'm here at the LA County Fair with the California Space Grant team from UC San Diego. I'm a senior studying mechanical engineering, and here we have Grace, a junior studying aerospace engineering, Haria, a senior studying aerospace engineering, Frank, a junior studying electrical engineering, Zoe, a physics student from Marston Middle, David, an aerospace engineer, and Dr. Kate, an aerospace engineer and professor at UC San Diego. We're going to start on the ride, so we're going to...
Hi, my name is John Kosmatka. I'm a professor of aerospace engineering at the University of California, San Diego. And what I'd like to do is just try to get you guys started and try to help you pull some of the stuff that you've learned in physics, pull that into what we're going to be doing today. So one of the first things that you learn in physics is that the fundamental property of mass is basically that it has mass. And so that if every particle has mass. And what we want to do is we want to separate the idea that mass is different from weight. And so on Earth, if you remember, weight is defined as mass times acceleration. So we look at the acceleration on Earth, and typically it's 32.2 feet per second squared, or you can think of it as 9.8 meters per second squared. So on the moon, gravity is much less because the moon is actually a smaller diameter. And so because it's less, effectively what you would weigh on the moon is actually less. And so the gravitational acceleration on the moon is only 1/6 that of Earth. And so you don't really, if you weighed 150 pounds on Earth, you would only weigh 25 pounds on the moon. So if you guys have got the video in front of you, can you click on the short video clip of the astronauts on the moon, and then let me know when it's done. So on the moon, the gravitational force is much less. The gravitational acceleration, is much less. And so you would weigh less. And so the next thing that we wanted to kind of get across is that if you're on a rocket or if you're on an airplane, as you maneuver around on an airplane, the acceleration is going to change. As that acceleration changes, then you either feel heavier or your weight is reduced due to those gravitational accelerations. So the idea we want to get across is that with the change in acceleration, then effectively your weight will either increase or decrease. Now, what happens if the acceleration gets too large? Does anybody have any ideas? What would happen if the accelerations became too large?
You croak. One of my students just said your insides get crushed if it's too large. Yep.
Very good. So what actually happens is as the accelerations become so large, effectively all of the molecules in your body, that weight keeps increasing. And what actually happens is that your heart then isn't strong enough to pump this heavier blood up to your brain. So the very first thing that happens after about 5 or 6 Gs, what happens is that your heart can't pump the blood doesn't get to your brain, and then you pass out. Sorry about that, a little problem that the temperature got so high here in Pomona that the phone shut down. So we were talking about basically that if the accelerations are extremely large, what first will happen is you'll probably pass out. And then if they got larger and you still passed out, then what your student said would be absolutely correct. That the forces and the effective weight would get so high that it would start to crush your organs and crush your body. So the final thing that I wanted to mention was that if the accelerations are chaotic, meaning that they change a lot, as if they're changing so quickly, well, your body's expecting it to be steady like gravity. If they change a lot, then what typically happens is your brain immediately assumes that you've been sick or you've been given a poison. So then what your brain will do is it'll trigger to your stomach and say, throw up all the food in your stomach because it thinks it's being poisoned. So that's why if you're on some of these rides and if you're not used to it and you find yourself getting seasick, this is typically what could happen. So the final thing I wanted to get across is amusement park rides are really designed to try to excite you try to give you a lot of these wild acceleration feelings, but they don't want to get you to get hurt, nor do they want you to get sick. Okay, so what I'm going to do now is I'm going to pass this over to another member of our team who's going to talk about how we measure some of these accelerations, and then I'll come back and talk a little bit more about what are the typical G-forces that you would get on some of these rides. All right, we'll see you in a little bit.
So please stop me, or if you want me to explain more. So we're going to actually, Zoe is going to do it. So if you guys want to start on it at the same time, it would be nice too. So what we're going to do is we wanted to attach the string to the cork that we have by using pin or anything that you have. Yes. So try to grab one side of the string and attach it to the cork. And when you do that, the next step that we wanted to do is we wanted to put the cork inside the bottle, which has water in it. Pardon? Oh, and in case that it's a full of water, then you might want it to empty a little bit of the water so that when we put the cork in, it doesn't split. So why don't you open the bottle and drop the cork into the bottle. And you want the size of the string that goes into the bottle after you screw the tip of the bottle to be when you make it upside down, you don't want the cork to touch the bottle. You want it to, when we make it still, not moving, we want the cork to be floating in the water. So try that. Okay, now let's see. Now it's too far. So what we're going to do is we're going to take out a little bit of the string, then screw it again, upside down. I think we need to do more.
A little more.
Yeah, do like half more. Okay.
There. That should totally be enough. Oh,
It actually. Okay, maybe a little bit in. Okay, there we go. So let's try to keep it stationary so we see that it is floating. And now what we wanted to do is we wanted to show the acceleration, which and the direction of the acceleration. By moving it to the right really quick, you notice that the cork is also moving to the right. If you go quickly to the left, you see that the cork is also going to the left. And that's the direction of the acceleration. Now, the fun part is the spinning. So I want you to spin it, the bottle. If you can see and notice, the cork has to move to trying to move to the center of the circle, the motion. And that's actually the direction of the acceleration when we have the circular motion. And there we go. So we talked about the acceleration, the very easy acceleration.
So what we're going to do now is we're going to have Frank, one of our top-notch stunt pilots. He's going to get onto the ride, and with the ride, he's going to basically be able to show some of the accelerations that he's going to record. On the front of him is basically a vest. On the vest is basically a device very similar to what you guys have, and this device can be used to basically record accelerations, and he can record it in basically three directions. So he's able to get the acceleration vertically, he's able to get the acceleration coming out of his body, and then the acceleration from side to side. So with this, we can basically compare what he actually feels with what you guys and what we can mathematically predict, so we can prove to ourselves that the equations are correct. This will help us to design much better roller coaster rides. Okay? Jump on.
See you good.
Okay, so I'll continue talking. What we'll try to do is we'll try to progress along the way. I want you guys to kind of keep an eye on him and tell me how he's doing, if there's any problems at all. We don't want him falling off. We don't want him getting sick. Okay, so
Hey,
have we been able... I'm sorry.
Yeah, quick question about that accelerometer. He has the actual sensor in his vest, right?
Right.
Okay, and as far as like the the computer or the device that's actually reading the data, does he have that too, or do you have that?
No, he has that as well. So within that vest, he has the accelerometer. It's a triaxial accelerometer measuring 3 accelerations.
Okay.
That's mounted in the vest. And then he has the actual system that's recording all the data. So when he gets off the ride, we can then copy that to a file. We can upload that then to something like Excel, and we can go ahead and plot it, and we can go ahead and look at the accelerations. What we do then is we take that acceleration, we divide it by the acceleration of gravity, which is 32.2 feet per second squared, and then that gives us our acceleration defined in terms of G's. Okay?
Cool.
What I would like you to do, and maybe encourage your students to do at a later date, is 1, look at the astronauts walking on the moon, and 2, we uploaded videos of some of the Air Force pilots who get trained on a centrifuge to see what their bodies look like as they go from 3Gs through 6Gs through 9Gs. And it's a very interesting video to see how your face changes under all of these loads and how many of these pilots cannot basically stay awake and they pass out under 5 to 6 Gs. The Air Force then trains them so that they're able to survive 5 to 6 Gs. So if their aircraft is going through a very aggressive maneuver, hopefully the pilot can stay awake. What I'd like to do now, while Frank is on the ride, is I'd like to try to get you guys to open up the first video, which is called Alien Abduction. So if you could open up Alien Abduction and play it, then what I'll do is I'll work through very quickly how these equations are developed and what we found. So on Alien Abduction, if you're watching this video, you're basically seeing that it's a large plate almost spinning around. What we effectively do is we have riders that are on this plate. As the ride starts to spin up, and I'm going to use capital omega as my rotational speed, as the ride starts to spin up, and because the rider is offset by a distance r, a radius away, what we get is a centripetal acceleration that's produced, A, and A is defined as r omega squared. And so with r omega squared, if we substitute in the speed of the rotation and the radius, we can calculate the acceleration that the rider feels. And what's happening is as he's feeling this acceleration, he has a general sense of his body wanting to move outward. And so we do know by talking to the manufacturer that this plate is spinning at 24 revolutions per minute, which is 2.51 radians per second. We also know that the rider is 15 feet away from the center of rotation. By doing that, I can substitute in for r, omega squared, and for g, and I can get that he is riding at 3 Gs. Well, I got to hold on a second here. Looks like Frank just came back off the ride. How you doing, Frank?
Everybody!
I'm not so sure he's going to make it. He's our second rider, second pilot. The first one didn't quite make it. He's still off the ride, but Frank has just survived. Frank, you want to comment on the ride?
Sure. I'm all ready. So let me get these headphones on real quick. Oh boy, my heart's still pounding. Oh, how's everybody doing? Can you hear me?
Yeah, we can hear you.
Okay, awesome. So how's everybody today? You learned some cool stuff about acceleration or about g-forces, about some science and physics. Is everything good? Yeah. Awesome. My little vest right here. I was saying, it's not a fashion statement. Like, this isn't very popular to wear something like this. But it's actually an accelerometer. I believe we showed it a little bit earlier. So I'm going to take it out again. So we actually use this accelerometer to record data because we're essentially running an experiment. So today I'm going to talk about data and then data analysis. So everyone on the same page here? All right, so I'd like to move on to the data that we recorded. So can you play that video, please?
Yes.
Okay, and I would like you to uncheck the Y and the Z boxes. So we will only be displaying the X information. In other words, the vertical G-forces. It should be yellow. Everything good? So you see, can you hear me?
Yeah, I can hear you.
Okay, awesome. So you should be seeing, I think I hear screams and such. So you should be seeing peaks and troughs as the video moves by. Are you observing the red line move across the graph?
Hi again, we're Julie and Zoe, and we have some questions to answer for you guys. So, have any of you guys thought about being a scientist or engineer?
Yeah, and actually, why did you decide to become an engineer?
Well, growing up, I really was into art and drawing, but I knew it was kind of hard to make a career out of that. And I also loved math, but it was a little too black and white and a little boring, so I wanted something more interesting and creative. So that's why I chose engineering.
And do you know who designs these rides?
So it's a whole team of engineers comes together to build these rides. So just like our team here, you need electrical engineers, mechanical, structural, aerospace. They all work together to come up with something like this.
Okay, and what's the process in creating one of these rides?
So first, the group comes up with an idea, but we don't want to build that idea right away because it might have problems and we don't want to waste money on that. So we start with a simulation. Then we go to a prototype and a model, and then we go further on to testing, and then we finally build the ride. Okay. Any other questions?
Where do you go to school?
What?
What school are you going to?
I go to UCSD, and I'm in Marshall College. I'm studying mechanical engineering.
Thank you.
Equations that you guys are deriving and using in your physics class are doing an excellent job of being able to predict what's actually happening, and that's exactly what we're measuring experimentally. And so this is a great help to you guys if you ever want to design roller coasters or amusement park rides in the future. You have confidence that these equations are working. So one of the last things we wanted to do today was to talk about this ride, which is called the Skyflyer. And Skyflyer is a very simple ride, and basically, if you look at what's going on here, I'm going to try to show you what an engineering rendition would be, and this is also on the video on the website. So if you get a chance to play that video, again, you'll get the same feeling. But basically, it's a disc that you're seeing is going to spin around, and then there's going to be chains that go down to a swing. And basically our rider, let's go ahead and put a big fat rider in there. This rider is going to be sitting right here, and he's going to be swinging around. And so what you're doing is going around and around and around. Well, from the manufacturer, I know this radius, I know this length, so I know the rider is 45 feet from the center of rotation. I also know how fast he's spinning. I know how fast he's spinning. So with this, again, I can use the same equation that we talked about before, and if I substitute in for the radius, the speed, and gravity, I can go ahead and do a calculation, and the calculation says that this rider, as he's going around, is going to be feeling 1.53 Gs. If you look at the experiment that we did on the website, you'll see that the Gs that were recorded were 1.5 Gs. So again, we get an outstanding agreement between what your equations are going to show and versus what we see experimentally. So there's a lot of confidence in what's going on. And again, what R omega squared is, this is the centripetal acceleration as a result of the person spinning around. Does anybody have any questions?
No.
Bye-bye. Bye-bye.